Thank you, everyone, for sparing your lunchtime to get a bit of a history about Excalibur Screwbolts and what we've been doing with the rail industry to date. So the title of our presentation is Excalibur Screwbolts, a modern approach to rail fixings, how we're hopefully improving rail productivity, reliability and workforce welfare. Can I have the next slide, please, Sarah? We'll go through an introduction of ourselves. It'll be myself, John Stevens, and our development engineer, Chris Parasram, doing the presentation. Product overview with a focus on the sleeper bolt, speed of installation video, and then the technical features, followed by a Q&A session. Can I have the next slide, please, Sarah? As Darren said, Excalibur Screwbolts were the original inventors of the twin helix thread, which will cut its own way into concrete. This design revolutionised the construction fixings industry, and we've been fortunate enough to win 2 Queen's Awards for Innovation, one in 2009 and one in 2016. Can I have the next slide, please, Sarah? The Excalibur Screwbolt fixes directly into a pre-drilled hole, giving immediate high load capacity. It can be a replacement for all types of traditional fixings, including expansion anchors, chemical anchors, large screws, plugs and pins. It's been used in all major building substrates, from concrete, brick, timber and plastic. It has enormous whole life costs and operational benefits. It's a proven product which is being extensively for both temporary and permanent requirements on rail, civil and track projects. Next slide, please, Sarah. In 2014, 15, 16, the Excalibur Plus bolt was chosen by Crossrail to meet its 120-year design life, and these fixings were used for the platform edge screen brackets, the GRC panels, cable management systems, amongst some other associated panels like the escalator barrels as well. So extensively used on Crossrail. Next slide, please, Sarah. Coming up to more what would be of interest to the PWI members, our track applications. From construction fixings, we were identified early on in our history for applications on rail, and they include special bolts for fixing down insulator pots for London Underground, special stud bolts for fixing down signalling systems for Alstom, and also some more standard products which are hex head for Pan 8 base plates and also 2-level base plates. Can we have the next slide, please, Sarah? Today's focus has been on our work with the introduction of our 20mm sleeper bolt for timber. So it was identified by Network Rail Improvement Specialist says that by adding the twin helix thread to a bolt that's similar in a dimensionally to replace the AS screw spike would be of benefit. So we looked upon doing that as a collaboration with Network Rail and also with London Underground helping out as well. So this is a sort of a discussion into what testing and what site benefits we found going forward. Can I have the next slide, please, Sarah? When we was approached about this, we were told loose and missing rail screw spikes in timber sleepers are commonly acknowledged problem on all rail networks worldwide. So here's, you can see a set of track with loose and missing rail screw spikes. Can we have the next slide, please, Sarah? The main issues with the traditional screw spike that dates back to Victorian eras is that it's splitting of the timbers at the surface. This is a common degradation for the sleepers and bearers using screw spikes. Counterboring in the sleeper is no longer carried out at installation, so the standard AS screw spike being tapered basically sets up surface stress fractures occurring during the installation. As these splits, shall I say, elongate under load, The screw spike loses grip, and it's exacerbated by vibration, temperature, and moisture. This causes cracking, splitting, more evident within tight curvatures, and excessive lateral loading, increased bending forces within the screw and the fixing hole. The solution Excalibur can offer is a design that requires no counter boring. Our patterned thread is much sharper and cuts into hard and soft materials, so offers less resistance when thread forming. The resulting wood fibres then become securely wedged between the threads, resulting in resisting withdrawal. Excalibur screw bolts require far less force to insert than traditional screw spikes. Can I have the next slide, please, Sarah? Here we show a video of Excalibur screw spikes being installed, but first of all, you will see the traditional AS screw spike being installed by Network Rail's team, Eastleigh Depot, Southampton University. This is all part of a ergonomics test conducted by Network Rail. So with the AS screw spike, because of the enormous amount of installation torque required, you will need to use big heavy impact wrenches with circa 2,000 Newton meters of torque to install this product. Next, we have an Excalibur timber sleeper bolt being installed by the same team of Network Rail, using a battery-powered impact wrench into similar density timber sleepers. As you can see, the results are pretty impressive. You're managing to install 3 Excalibur sleeper bolts in well under the time that 1 AS screw spike would be installed. So in summary, they are quick and easy to install, giving time savings, improved productivity and workforce welfare. So the video is there. So can we have the next one, please, Sarah? You will also see from this slide that where you install an Excalibur, which is on the left of the slide, you get very minimal installation damage. Whereas when you install an AS screw spike, you would normally not see this because the base plate will be over the top of it. You get quite significant installation damage. You'll note that the AS screw spike on the right hand side is not fully set, so there's still more damage to occur on that sleeper. Can I have the next slide, please, Sarah? As I said before, we came up with a design which was given to us by Network Rail measurements for the bolts, so is effectively a virtually similar copy as the standard screw spike. So it's take the same application basically. Can I have the next slide, please, Sarah? Just going back to the Victorian era and the rail industry, obviously they've moved on now from steam trains to electric trains, now maybe hydrogen trains. Track fasteners, for holding the track together have moved on together, but as you can see, these date back to 1890. Large screws are still being used to fix timber sleepers down. So yes, that's 134 years old now. So this is why we're saying Excalibur would be a modern alternative for you. Can I have the next slide, please, Sarah? I'll now hand over to Chris Parasram, our development engineer, who will go through some of the technical details, the stress and strain gauges, installation information that we gained from tests we did at Southampton University. Over to you, Chris.
Good afternoon, everybody. This isn't going to work quite as easily as I hoped it would, because I was hoping to use the laser pen pointer. So I will try and briefly describe what you're looking at. So these tests are conducted at Southampton University in connection with, obviously, Network Rail and Excalibur Screwbolts. What you're looking at now is the bar chart representation of 5 tests of each type done as a comparison test. So it's 5 tests of AS screw spikes and 5 tests of Excalibur 2163 chair bolts. This is a strain measurement of the bolts being inserted into the hardwood timber. The test basically is a pre-drilled hole. 6 sensors are placed at 90 degrees to the hole. So 3 sensors will be running with the brain and 3 sensors run across the brain. In this chart, the blue bars that we can see, can you see the mouse pointer moving?
Yes, we can.
Yes, Chris, we can see it.
Right, that makes it a lot easier for me then. Okay, so what we're looking at here is these blue bars represent the AS screw spikes, and the orange bars represent the Excalibur chair bolts. So the sample specimens are all across the top. Each one's ID'd across the top. And to the left-hand side down here, what we've got is the strain that is imposed in the surrounding timber. So if you look at basically, you've got the worst reading that Excalibur sort of achieved was 547, and the worst reading that the AS made was 1487. So what we're looking at here is this bar here represents the average mean of 1068 for the traditional AS screw spike, and what we're looking at on this bar here, it's the average mean for the Excaliburs at 247. So what can we take from this graph that we're looking at? Straight away, this starts to tell you why you're needing you know, a petrol powered type machine that will generate 2,500 Newton meters of driving torque. So that starts to answer the question about why you need such powerful tools, you know, and obviously with that you've got the halves issues and you've got the cost that comes into it. So can we go on to the next slide, please? Right, so what we're looking at here now is individual tests from, these are individual test results from the bar chart you've just been looking at. So what this shows again is across the top, it's specimen AS3 that we're looking at, the installation. So what this has got across the top is time in seconds. Both charts are identical in the scaling and the way they're done. And to the left-hand side of the chart, we have got the strain being imposed to the surrounding timber. So first of all, we'll look at this chart. So this is your traditional AS screw spike. What can we take from this chart? Well, from this chart, we can take that it took about 12.5 seconds to fit. So we know that because when the spiking stops and it starts to flatten out on the lines, we know that's where the point that the bolt was inserted into the timber. So from this, what we've got is it's been left running and you've got another further 15 odd seconds of flat lines. What these flat lines are representing is the strain that is remaining in the surrounding timber after the bolt has been fitted. So from this also we take that at this point here, this is recording something like 1487. When you drop down to here, you're roughly on a figure of about 324 at this point. So what this suggests is these lines will not drop back to zero. Zero is no strain, so this line along here represents no strain. for these lines to drop right back to this, the only way this is going to end up back down here is if the timber splits. So hence the use of gang nail plates and all sorts of things like that on the ends of timbers. But you also have to have a fairly good edge distancing to have half a chance to make the traditional AS screw spike work. So when we compare now the Excalibur, remember that the graphs that you're looking at are on exactly the same scale. So across the top is time in seconds, and down to the left-hand side is the strain imposed. So for the Excalibur, we see, as the bolt is being inserted, we see a maximum of 247 is recorded as a value that it peaks up at. So we can also take from this, the fitting time is approximately 6 seconds, because we're at this point here where the lines start to flatten out. But the interesting thing more so is, after the bolt is fitted, although it hasn't been allowed to keep recording for many seconds afterwards, it's literally about 4 seconds it's been left running for afterwards. But if we know, remembering that 0 is no load being imposed to the surrounding timber, so if we note where these lines are now after the bolt is inserted, they are all but back on the 0. So if we said worst case scenario for this, the lowest value for the traditional AS screw spike, if we said that was 324, the maximum amount of strain that the Excalibur is imposing, well, once it's fitted, is less than the minimum that the traditional AS screw spike is imposing. So from this, what you can take is that there's going to be a lot less chance of the timber splitting and bursting. For that reason, at the end of the day, that will also allow you to fit closer to the edge, and also on a shorter length as far as the grain goes. Right, can we go to the next slide, please? Right, so we've learned basically why you need to use such a powerful machine to install the bolts. We've now got more of an understanding of why the timbers split. So now what we're going to look at is the cyclic loading. So these lab tests are a representation of, I believe it's Class A and Class B track scenarios. The cyclic loading is done to represent the wheel interaction with the rail and the stiffness of assembly. So all of these tests that we've been conducted have been conducted to, just get the numbers for you for those that are interested. Right, so the testing, for those that are interested and want to learn more about it, was done to BSEN 13146 and BSEN 13481. So we're now looking really at this graph is showing us about what happens under cyclic load. So this scenario here is basically within the standard, let's say, that is set for the class of track that it's meant to run in. So we'll say AB. What we're looking at across the bottom, it tells you how many cycles have been run and what the vertical loading is. To the left-hand side of the graphs, it is showing you the amount of movement where the bolts are unscrewing, measured in microns. So we start off with a basic running in period, which is this. So what we see here, it's run 600,000 cycles, about just over 100 kilonewtons in vertical load, and the lateral load at that point is about 20 kilonewtons. So this starts to represent the loading that the wheels and the flanges would load onto the track. one thing that is worth noting, all the components used for this were all new components. So in that, you've got a new piece of hardwood, you've got pan 11 base plates, you have got the AS screw spike, you've got the Excalibur screw spike, new ferrules, new pads, new clips, and they support basically a piece of rail about 250 mil long, and then at a varying angle, the living daylights is knocked out of that rail. That's how the test worked. So getting back to what you're looking at, here is the blue bars represent the AS screw spike. So we've run 600,000 cycles, and we call this the running embedding down period. That allows everything that is going to move about to settle down and take its position, basically. So at this point, we can see that the blue bar, which is the AS screw spike, has started to unscrew, and it's made at that point about 45 microns. But there's no orange. The orange represents the Excaliburs. So the Excalibur did nothing. It stayed where it was tightened to. So we then move along to 1.2 million cycles, which is here. 120 kilonewtons on the vertical loading and 23 kilonewtons on the lateral loading. So what do we see? What we see is the Excalibur has started to slightly come undone. It is still well under 20 microns. The traditional AS screw spike has reached up to about 70 microns at this point. That's on. So test runs on. We run up to 1.8 million cycles. At this point here, it's 130 kilonewtons on the vertical loading and 24.9 on the lateral loading. So from this, we take again the traditional AS screw spike. He's happily coming undone, and it's reached the point that it's on somewhere around 90 microns. Traditionally, screw spikes come undone. We sort of know that, and that is expected really of any fixing under the circumstances. But the Excalibur, the orange bar, we're still well under 20 microns. We run on to 2.4 million cycles, 140 kilonewtons on the vertical loading. The lateral loading has become 26.9 kilonewtons. So what do we see again? Again, we see the blue bar is moving up a little bit more. It's just over the 100 micron in movement compared to the Excalibur, which is still under 20 microns. So we move on to the final part of the testing. So this is 3 million cycles. This is run now. The vertical loading is 150 kilonewtons. The lateral loading is 28.8. So under the prescribed BS standard, you go from virtually nothing to about 30 kilonewtons for the lateral loading. So this test that we're looking at here is to that standard. So what can we conclude from this? Well, what we're looking at here is the AS screw spike has unscrewed to about 107 microns. The Excalibur in this test has gone to about 16.5 microns. Remember, this line here is 20 microns, and we haven't even reached that. It's still shy of it. So this test that we're looking at is the prescribed for the BS standard that it relates to. So because we wanted to try and induce failure, one other thing that is worth noting is that in both of these tests, because we wanted to try and induce failure, instead of the load going on a pan 11 base plate into the 2 bolts, which it would naturally when you've got it set in track, it was turned round to force the load into the singular bolt. So it's set into a frame, and the frame is angled appropriately to allow the cant to go that way. That's how it's done. So on the second graph, we wanted to get something to break. We want to see failure. Whatever fails, we wanted to see it. So what you're looking at here on this graph is basically it's an overload. So this goes out of the prescribed Class A, Class B, but for the reason that I just explained, that's why we did this. So what it is basically is we start off with a running in period of 900,000 cycles it runs for, with 100 kilonewtons on the vertical loading and just under 20 kilonewtons on the lateral loading. So we run this. When you look at this, what this is showing is the Excalibur's come unscrewed and it's made 55 microns at this point. But look, there's no blue representation. So the traditional AS hasn't moved. It stayed where it was. On this graph, the difference is 0 is the set point. So if we'll remember that, that was where the bolt was tightened to before the test was run. So we run on to 1.2 million cycles, which is this set here. Now, we've got the AS has lifted 20 microns at this point, which is what the blue bar represents, but there's no orange bar. So where's the orange bar gone? What this is suggesting is that the Excalibur has now tightened up under this loading back to its original set point, because there's no representation of the orange bar, so it's disappeared. At this point, it's 150 kilonewtons on the vertical loading, which is basically full tilt. And on the lateral loading, it's ramped right up to just under 30 kilonewtons. And we then move on to 1.8 million cycles. Now we've got a little bit of representation. The Excalibur has started to appear again on the bar chart. It's lifted 4 microns to compare that against the traditional AS, which is now on 39 microns. So we move on again towards the end of the test, where we've got 3 million cycles it's run, still 150 kilonewtons on the vertical loading, and still maximum just under 30 on the lateral loading. So this has been flogged to death, basically. What do we see? Right, well, remember that this line here, 0, represents where the bolt was originally tightened to. What this is showing us is that for the Excalibur, the orange bar, it's gone beyond where it's tightened, and a value of 24 microns was recorded for this. When you look at the representation for the traditional AS screw spike, you've got 114 microns of lift in this time. So that is comparable to what we saw in the first set of tests. Now, this testing could possibly suggest fit and forget, but we can't say that for sure, because we would need to run more tests to verify this. So this is an anomaly that is very rarely seen. In my working life, which is 40 odd years, I've never seen this. Most things mechanically will fall apart subject to vibration and that. But it's interesting to think about this scenario that you're seeing. That there is a chance that this could be shown as a representation of instrument error. But one thing I would say is that the method of recording all the data and that basically was used DTIs, which are obviously the traditional method of measuring movements and stuff like that, and also a smart strain gauge system that the university employs. So 2 methods of recording these movements were literally taken. But take what you want from this. At the end of the day, the one thing that is worth taking from it is that any movement that does occur, so if we look at the original testing, is significantly less for the Excalibur screw spike compared to the traditional AS spike. So can we go on to the next slide? Right, okay, so what we're seeing here is, as part of the testing, this is a tensile load test to measure the resistance, the force of resistance that the bolts will support. Now, what you can take from this picture is, if we look at the destruction that's occurred, so this is the traditional AS screw spike, and if we look at how much damage that has done to the face of the timber, it is possible to see. So the Excalibur, basically, it has damaged it because you are tearing the bolts out. Literally, that's what you're doing. So you can compare that. To give you an idea, when we're talking about the strain gauges, these are the 3 strain gauges going across the brain. There's another 3 that you won't see in this picture that are set behind that run along with the brain. So maybe that helps you to understand a bit more about how the tests were conducted. But what all of this is showing you is what you do not see. So when you fit AS screw spikes with ferrules, put the chairs down, the damage that is caused, which was shown in an earlier slide with the picture of the bolts, you do not see that because it's covered and hidden by the chair. But when you go back many years later and the timber split, you'll get a conical shaped funnel type hole around the bolt if you use a traditional AS screw spike bolt, and that purely happens because of the damage that's been set up as a new asset when those bolts are used. Food for thought, maybe. Can we have the next slide, please? Right, so again, these are samples that were taken, sample pictures were taken at Southampton University. So the picture on the left here that we're looking at is obviously the insertion of Excalibur 2163 chair bolts. Now, the Excaliburs have got a little tiny taper on them, and the taper is only used to moisture seal the holes to stop the water from getting in. So the little taper, this one has worked well because you can see it in the picture. The little taper is this representation here, and that stops any moisture from running back down the bolt into the timber itself. So this is what the Excalibur does, right? Here's a close-up, and you can see it again. It forms a slight little cone, which is formed off the taper of the bolt as the taper nudges into the top of the timber. But if we look at the traditional AS screw spike, it's made the hole a bit messy. So what we can see here is where the shank is being sunk down into the timber. You can see the mess that obviously it's created around the top of the timber. It needs to sink in a fair distance to obviously make it work to gain the clamping force, you know, via the ferrule and the chair and everything else. But also, even in this, you can start to see the split starting to appear. Although, in fairness, what I will say for this is timber being a natural grown sourced product, it does have some certain amount of splitting to it anyway. So, but in time, I would expect this to become a bigger rotted out cone, and these splits, if this is running out to the end of the timber that way, there's a good chance that will split right the way down the length of the timber to the end of the timber, hence the use in the past of gang nail plates to hold the grain together on the end of the timber. On this picture here, we're looking again at the insertion and the extraction of AS screw spikes, and again, you know, it doesn't look good for the timber. So maybe that helped you to start to understand why, for say, you people that are doing the maintaining and stuff like that out there, why you end up seeing what you see years down the line. What Excalibur's trying to do is to offer a solution which, for say the likes of London Underground, where you're fitting into pit blocks close to the edge on the ends of timbers and stuff like that, this is the best solution and ideal for those scenarios. And in the graphs that I've just shown you, that they're the explanation as to why. If for say like Network Rail, where space isn't so much of an issue, you can put in slightly longer timbers or whatever you need to do. Again, if you can not set up the damage when you're building your assets in the first place, how much longer will these assets last in the future? It will be significant, because you're not loading and straining in the same way with an Excalibur as you would be with a traditional AS screw spike. So from my point of view, the technical point of view, that's what I would take from the graphs that you've seen. There is a lot more to this testing, but unfortunately, I don't think we've got the time to be able to keep going into more of it. But any questions that anybody wants to ask, certainly come back and ask me. I'm going to hand you back, if we can go to the next slide, I'm going to hand you back to my colleague John, and he will explain the refinements of it.
Thank you, Chris. Hope everyone enjoyed going through the technical differences between the two products. And so from our perspective as well, it was asked by Network Rail to do who did a full ergonomics test comparison at the same time, and also did a cost benefits analysis based on. Hello. Can everyone hear me? I presume, hope so. So part of that analysis of the ergonomics tests and the product performance is based here in a Pew matrix, which comes out with the option 2. The Excalibur has a higher overall rating and better value for money overall for all the performance elements. Can I have the next slide, please, Sarah? So just to summarise really, and perhaps we can get on to Q&As, what people like. The Excalibur sleeper bolt is faster to install, it takes less effort to install. This provides improved productivity, extended sleeper life and repair costs, improved safety and reliability through its vibration resistance. It can be fixed using battery powered equipment, so petrol powered impact wrenches can be used, but they are, do not need to be used. So again, part of this process was based on workforce welfare, to help reduce HAVs exposure to operatives. If you're not using a petrol powered impact wrench, you've got no cosh exposure. Manual handling and workforce fatigue is also massively reduced. The Excalibur screw bolts are designed and manufactured in the UK with, say, associated production control, quality assurance, environmental impact and sustainability, whilst adding to the circular economy and carbon footprint. Network Rail and LUL have done whole life cost benefits analysis that are positive on the product. Both Network Rail SME action plan, in combination with the government's rail sector deal, is committed to developing a safe and sustainable UK rail sector at home and abroad by encouraging innovation, supporting British SME growth through collaboration and implementing intelligent procurement processes which value whole life costings. And we believe Excalibur screw bolts, and particularly the timber sleeve bolt in this application, do just that. So that is the end of our presentation. Hopefully you found it of interest, and say, Darren, if you could take over now, and obviously we'll go to a Q&A session.
Thank you, John. That was very useful. Thank you. so far, can you hear me okay?
Yep, it's fine, Darren.
Okay, brilliant timing from Justin Lewis. First question in. So reading out from the chat, if anyone wants to go into the chat, does the Excalibur screw use the same socket size as the AS screw, so the installer doesn't need 2 sets of sockets?
Well, no, it doesn't, because we were asked at the beginning of this to use what was standard for, modern fixings, which is a hexagonal drive. Everything, if you look through all your fixings you'll use in construction or in the home, basically, you would use hex, and because you get a better purchase power with a hexagonal head drive than you would do with the square type. So really, you are talking about a piece of equipment that's probably £20 to buy, standard off the shelf. It shouldn't be a barrier to using the product, I don't believe, because obviously the drives that the railway industry use are specialist. You'd have to go out and buy them. Part of the case study we had done with Wales and Western was that we don't have to go out and buy a specialist socket. We can just get one off the shelf, basically. But it is also aids the performance of the products as well. It stops it from your machine bouncing around on the top of the impact wrench, basically, because obviously the square socket. So no, it doesn't. But there are good reasons for that, and we were asked by Network Rail's, say, senior reliability improvement specialists at the beginning of this to use a hexagonal head, if that would aid the input, because obviously you looked at our products and why are you using a hexagonal? Why are we not using a square head? Well, square heads go back to the Victorian era where they were forged in fire, but they don't work very well in driving a product in. Basically, you've not got as much purchase points, and they don't provide the benefits on that analysis. So that's why we use a hex head.
Thanks, John. Yeah, metrification as well, I guess. So apologies if I've got your name the wrong way round, but Korabsky Wladyslaw did ask about how about composite sleepers? Have you done similar testing?
Right. Well, we've started doing testing with the new materials and obviously the new base plates that are coming about. Not so much official testing, but we have had some good results for Send Test C, I think it was.
To answer your question, Darren, or sorry, to answer the question that's posed, we have done testing into composite sleepers, but as I say, we focused, the original tests were focused on getting the product approvals for the timber sleepers. So as far as we're aware that anything that's got obviously approval into timber sleepers also has approval into the composites. But we've done lots of tensile testing, as Chris said, some Send testing for specialist applications as well, and effectively the same problems will arise into plastic as do arise into timber. Whereas you are getting basically damaging of the substrate, and with plastic it's slightly different. Instead of splitting, you get a bulbous lump appear at the top of the hull, basically. So it's the problems. What I'm trying to say is that basically you'll get a good fix with the Excalibur without all the additional problems that you have in with the screws. The screws will effectively get the same type of fix by forcing their way into the hull rather than cutting their way into the hull. So it's all a case of we believe that you'll get extended life out of if you fit an Excalibur into a plastic sleeper as you would do into a timber sleeper. So hope that helps.
Yeah. Okay. Unit cost comparison. Was it just the screw itself, or did you look at the installation cost and the speed and so on of installation? Did you consider that in your cost?
That was all considered in the whole life costing package. Yes. Yeah. That's something that was taken into account. We are more expensive as in the unit price, but I think, you know, Darren, when you look at it into S&C as a component part, particularly where this is where we feel, you know, is, you know, best to be used initially, shall we say, for new build S&C, where you've got all new components. You're spending multiple thousands and thousands of pounds for these, and so to pay a little bit more extra for, we believe, a better quality fixing would make sense. If you got possible, you know, extension of your asset by 10 years, you know, when you're out on site, your possession time. And so we've got a couple of case studies that we can show. I don't think we're going to have the time today, but can certainly send to anyone that's interested, where Wales and Western installed circa sort of 2,000 of our bolts, and they reckon they saved themselves about 3 hours in time by doing that over their measurements on site. You know, site is different to test scenarios, as we all know, but you know, in their analysis, they looked at how long it took them to install the AS screws button in comparison to our bolt, and so that's a significant amount of time, and obviously time is money. Doing other jobs, also, you know, confirming that, you know, it's a lot quicker and easier, so the workforce fatigue is lower, exposure to HAVs is lower, and all these things. So we also did a one-off case study with Charing Cross, Kent and Sussex, where they used longitudinal bearers, and that again showed significant time savings, no splitting of the timbers, you know, which it's all mentioned so on that side. So don't take it from us. Basically, have a look at a couple of the real life rail case studies, and hopefully you can see other people's opinion on it. And you know, what we ask is hopefully people just have an open mind on it and give the product a go, and hopefully they will see the same benefits.
Okay, quick one from Dominic. Whilst the socket to drive the screw can be off the shelf, you surely would prefer using an impact socket rather than a standard basic chrome vanadium socket.
Yes,
yeah, there needs to be an impact socket, but yeah, impact sockets are off the shelf basically. So sorry, I meant to say that.
Yeah. I think what we mean here is that you can use a Milwaukee power drill or any other power drill rather than an impact wrench, which is a very lumpy and damages your back when you're trying to lift it and operate it.
You can use smaller battery powered product rather than
to drive in.
To drive. But I think most of the companies now are going to battery powered stand up versions for the rail industry, aren't they? So that it's what I can see, but either or either will work.
Brilliant.
So, one other thing to add to that, if you're talking about battery powered tools, effectively with the Excaliburs, you'll fit more Excaliburs per battery charge than you will AS screw spikes, if that helps.
Yeah, that makes sense, Chris. Yep. Quick one from Oliver. How does Excalibur bolts perform in worn sleepers? Would there be a benefit in using them to replace loose bolts, screw bolts?
I think you need to determine what you're calling a worn hole. From this, yes, if it's replacing an AS screw spike, it will work to a certain extent, but you're never going to get the best out of it. We are looking at making a maintenance-sized version of that, which would be a maintenance-sized version of an AS screw spike. For the moment, it's semi on hold because we need to find out, obviously, whether there's going to be an appetite for this or not.
And anything that's going into a worn hole is always going to be an unknown, basically, and only the operative who's put in can see whether it's got a good fix or not, really. You know, because there is no definition of, and there never will be. Every hole will be different on
a test spec.
Yeah,
I think you need to agree a test spec for a worn hole, which isn't difficult to, so you can actually have some comparable results rather than because it's a bit varied. Thank you. Right, Mohammed, any dowel match with Excalibur for concrete bearers or sleepers? Any dowel to Excalibur matching, you know, as a system for concrete fixity? Guess the answer is it doesn't need one.
It doesn't know. It can go
No.
straight into concrete.
Yeah. Straight into concrete.
Yeah.
Those particular bolts, because for network rail you've got high grade, low grade, so you've got about 5 and then 8.8.
Yeah.
Realistically, 8.8, no, it's not hard enough to screw direct into concrete, but we can make them hard enough to screw direct into concrete on request.
Yeah, well, today's presentation was particularly about the bolts going directly into timber or timber sleep. It's all now plastic sleep moved on, but into softer materials. The Excalibur screw bolts start out life as the original concrete direct fix into concrete, so the twin helix. But so most of all our standard products work in concrete, and that then hence work down into, but in this instance, these are all specs that were handed out to us by the rail industry, Network Rail, London Underground. As Chris said, Network Rail start off with 5.5 and then their high tensile is 8.8, whereas London Underground use all high tensile 8.8 products. So there's not a difference there on that side. But I think probably as a business, we will stick with one 8.8 grade product to supply everyone, then everyone gets the best quality one. Basically, there's not a huge amount of difference in the. It's a heat treatment process for both of them, basically. So from a production point of view, either or either. So you might as well make the better one.
Okay. Kim's asked, is it possible to share the test report from Southampton University?
Who is that? Sorry.
Kim Spence. If you want to take her details from Teams.
Yes, please. Yeah.
So Kim can have. Gareth's jumped off. Thanks, Gareth. Kruger, pull-out forces for screws haven't been shown in numbers, just the damage caused, to be able to compare. But are holes for AS screw spikes not just much tighter to give a better pull-out resistance and naturally will increase the strain on the host material, i.e. by design? What is the purely vertical pull-out force requirement for screws, and how do both measure up to this?
Right.
That's 4 likes.
Right. First of all, then, the Excaliburs will take up to about 400 Newton meters of driving force to fit them into the hardest of timbers, and that is not using a lubricant or anything like that. The hole sizes that you drill are identical. So for hardwood timber, they will both be 19mm holes, for whether you're using an AS screw spike or whether you're using an Excalibur screw bolt. Because it's only 400 Newton meters roughly of driving torque that's required, that is what allows you to use small handheld battery powered tools. Now, the difference between the Excalibur and the AS screw spike is the AS screw spike is slightly tapered, whereas the Excalibur is a parallel bolt. The Excalibur, it cuts its way in, not forces its way in. So basically, the Excalibur has a sharp thread on it, which allows it to cut, whereas the AS has a blunt thread, which all it can do is force its way in. Hence, the graphs that we've been looking at with the strain gauges, that's what you're seeing, and that's what's causing all the issues that you deal with later on as the asset starts to age. Hopefully, that comes up over to you in those few graphs that I tried to explain and show to you why what you're doing is so difficult, why it becomes so destructive, and obviously you can figure out what the end results are, because you guys and that have to go and deal with sorting it all out when it all starts to fall to bits.
I think also, Chris, to answer, and John actually to answer the last part, what's the vertical pull-out force requirement?
If I go back historically, Darren, so I think you know this about this as well. When we were approached by Network Rail and also the historical mark we were given was 30 kilonewtons as a pull-out load, tensile load to be satisfactory for this. So we entered into the test at Southampton University, knowing after doing in-house tests, knowing that our product would perform better than 30 kilonewtons. But we also knew that from testing we done in-house that the AS screw spike would outperform that, which it does. The test at Southampton Uni was 75 kilonewtons on average for the A. And was it 115? For 115 for the AS screw spike. But what the tests identified was the method of how the two products are fixing themselves into the hole. Whereas Chris has just said, the AS screw spike is forcing itself into the hole, damaging the hole, getting a fix at the top of the hole, and then will fail dramatically when it fails, or cause the substrate to split. The AS screw spike is cutting its way in. Sorry, the Excalibur screw bolt is cutting its way into the substrate, and therefore not setting up. So, we've well exceeded what was the ask, shall I say, on the specification. We haven't been notified. Well, so we've had notification that there's other standards coming out maybe, but basically what I'm trying to say is that the tensile load is more than satisfactory for the application.
One thing I'd like to add to that before you move on.
You've got 1 minute, Chris.
Well, basically, if you've got a 3-bolt chair, you're talking about gaining a clamping force of nearly 22 tons. If you're using a 4-bolt chair with an Excalibur, you're talking about gaining a clamping force of up to 30 tons per chair. So does that help?
Yeah, I can explain where the 30 came. I can explain where the 30 came from, but we haven't got time.
There's a lot of water under the bridge on this one.
Well, isn't it, in concrete?
So quick one. We've got so technical data. Are there any technical data that you can share? Tensile shear loads? Because I know you've got a technical data sheet. Can you share that as well?
Oh, we can share a technical data.
We'll work out how to share it afterwards. But yeah. Maybe if you take down the chat details on this.
All I would say, Darren, before anyone goes about, there is no technical data sheet for an AS screw spike. There was no testing for the AS screw spike until we did the testing in comparison. So, people are asking us for data. There is no data on the existing. It's just got grandfather's rights and has been used. There is no. So the RIPW drawing does talk about a few things, but it's a BS64 standard, which is very old. But there is a new specification coming out for chair screws and bolts that is being drafted by a member of our technical authority team. So watch this space. We saw one a little while back, but I don't think that ever got to.
I guess a parting one from Mike Andrews. You don't need a maintenance screw, as you can use Spike Fast. There you go. Spike Fast doesn't need maintenance screws. And all that repair damage. Yeah. Anyway, right. So I'm going to try and summarize this. That was brilliant. Really good engagement from everyone viewing as well. We had up to 86, I think 85 people. So that's really good. Lots of good detail as well about the testing from Southampton. I think the beauty of this, or what, if we can, it would be to try and share the technical data and a lot of this slide pack, so we could probably send it out to as many people as possible. Don't know how we'll do that, but I'll ask my colleagues back. But overall, I'd just like to say round of applause. Thank you very much, John. Thank you very much, Chris. Really good. And hopefully everyone enjoyed it. And tune in 2 weeks' time for the next one.
No, thank you for everyone giving up their lunchtime, and so hopefully it was helpful. Thank you, everyone.